So our next speaker is Professor Tehshik Yoon from University of Wisconsin-Madison. Professor Tehshik Yoon received his undergraduate degree at Harvard in 1996 under the mentorship of Professor Dave Evans, and a master's degree at Caltech under the mentorship of Professor Eric Carrera in 1998. Tehshik then became Dave McMillan's first graduate student, first at Berkeley, and then at Caltech, where he earned a PhD in 2000. Tehshik returned to Harvard in 2002 and did a postdoc with Professor Eric Jacobson as an NIH fellow. Tehshik has been on the faculty at the University of Wisconsin-Madison since 2005, where he is a professor in the Department of Chemistry. Professor Yoon has received several prestigious awards, including the NSF Career Award and the Alfred P. Sloan Research Fellowship and the Camille Dreyfus Teacher Scholar Award. Let's welcome Professor Tehshik Yoon.
All right, well, thanks very much for the introduction. I want to start, along with everyone else, by thanking the organizers here. I'm oddly nervous about this because I am aware of the grand history of the National Organic Symposium, and to be part of this tradition is really special and wonderful. So thank you for letting me be part of it. Thanks to the local organizers for this fantastic venue. Thanks to all of you for being here. I know I'm the last thing between you and lunch, so hopefully this will be good. So I want to tell you today about a problem that my lab has been thinking about for about a decade now, and that's the control of stereochemistry and photochemical reactions. So the reason that my lab has been interested in photochemistry for such a long time, I guess really comes from the fact that I learned about photochemistry as an undergraduate. And I was really captivated by the fact that photochemistry seems to break all of the rules. Right? So if there's anything that we learn about photochemistry as undergraduate students, it's that the reactivity that you get by thermal activation and photochemical activation is often very different from one another. So we learn about that first in the context of electrocyclic ring closing reactions under either thermal or photochemical conditions. These are beautifully stereospecific reactions, but one gives you conrotatory ring closure, the other gives you disrotatory ring closure reactions. I was even more fascinated by the fact that you can get different chemoselectivities under photochemical and thermal conditions. So Phil talked in his lecture about how the Diels-Alder reaction is among the most academically well-studied reactions, and this is for a variety of reasons, but there's a lot that we understand about essentially everything having to do with the 4+2 cycloaddition of dienes with olefins under thermal conditions. But the Woodward-Hoffman orbital symmetry requirements also tell us that the same reagents that one would use in a Diels-Alder reaction under photochemical reactions don't undergo 4+2 cycloadditions, and instead you get 2+2 symmetry-allowed photochemical cycloadditions to give you these vinyl cyclobutanes. So in fact, photochemistry is perhaps the most straightforward way of making these unusual strained ring systems, molecules like cyclobutanes and oxetanes and so on. And so I'm really interested in the fact that photochemistry gives you certain kinds of synthetic capabilities that are unique to photochemistry and are very difficult to replicate using other kinds of catalysis. So this becomes important when you think about what it is that synthetic organic chemistry is really good for in a broader societal sense. So I'm showing you here the structures of some of the most commonly prescribed drugs in the United States. A couple of them are natural products, like this one and this one and this one, of course. But by and large, the vast majority of compounds that are prescribed as life-saving drugs in the United States and across the world are synthetic compounds that have been discovered by synthetic organic chemists who synthesize them and hand them off to somebody else who tests their biological properties. So one way that a synthetic organic chemist gets inspired by the diversity of structures in drug molecules is to look at these compounds and ask, well, what are the most common substructures available in these molecules? And can we come up with better ways of synthesizing them? So some of the privileged pharma, of course, that I think we all recognize now are nitrogen-containing heterocycles, for example, stereochemically well-defined arrays of heteroatoms that can bind well to enzymatic receptors. So of course, my group also thinks about these sorts of problems and tries to design photochemical strategies for the synthesis of these privileged motifs. This is an oxyamination reaction we've been working working on recently that's not published. It's a photocatalytic reaction where this nitrogen and this oxygen add across a double bond to give you these oxyamination products in good yields and good diastereoselectivities. So certainly that is a valid and active way that we get inspired by drug compounds to develop new methodologies. But I think there's another equally important way of being inspired by the structures of common drug molecules, which is not to ask what the most common substructures are, but rather to ask what are the structures that are missing. And so let's think for a moment about cyclobutanes, these compounds that I said are uniquely available via this 2+2 cycloaddition reaction that's arguably the most sort of prototypical photochemical reaction known by most organic chemists. And you'll notice there really aren't a lot of cyclobutanes in drug molecules. In fact, the last time I looked, there were 7 drug compounds that have been approved by the FDA that contain cyclobutanes in any context. So, there are a lot of reasons why 4-membered rings might be missing from drug molecules. They could have terrible biological properties. They could be chemically unstable. They could have bad PK properties or whatever. But another reason why we might not have cyclobutanes in drug molecules might be because the chemistry for the synthesis of these compounds, especially under controlled conditions, is not nearly as well developed as that of making other ring systems. And it's a truism that if you can't make a thing, you can't test it for new biological properties. So to figure out what it is, whether it's the biological properties of cyclobutanes or the synthetic accessibility of these compounds that really is responsible for the lack of those rings in these compounds, you can also analyze another set of bioactive molecules, in this case, natural products. And so they're on the order of about 2,000 known natural products that contain cyclobutane rings, which is a lot. I mean, it's a surprisingly large number. And they really come from everywhere. So this one comes from trees. This is an insect pheromone. This one comes from sponges. This is a laterane that makes up the cell membranes of archaeobacteria. This one comes from yeast. So they're everywhere. There are a lot of them. They come from monocellular organisms and polycellular organisms, from marine organisms and terrestrial organisms. So clearly, nature knows something about the chemical biology of cyclobutane-containing compounds, such that it's willing to invest 20 to 25 kilocalories per mole of strain energy into the syntheses of these 4-membered rings. And so a question you have to ask is, well, if biology is synthesizing these cyclobutanes because there's some biological benefit that they provide to the organism that synthesizes them, but we don't have the chemistry to replicate that kind of robust synthesis, then what biological activities are we missing because we're not using photochemistry to synthesize these compounds? So I guess an obvious question then is, why is it that photochemistry hasn't been used very commonly amongst synthetic organic chemists? And I think there are a couple of reasons. One of them is a completely trivial reason, which is simply the accessibility of the equipment that you need to run traditional UV photochemical reactions. So this is our Rayonet reactor. It's the sort of standard go-to equipment for direct photolyses using UV light. So of course, all of you know that organic molecules in general are not strongly colored, and so they don't absorb wavelengths of visible light. And so to activate an organic molecule, typically you need high energy UV light, and you need some sort of photoreactor that's capable of generating UV photons in an efficient manner and then containing them safely. They're not that expensive. This Rayonet reactor costs on the order of about $4,000. For the students in the audience, that's about the same cost as a brand new Rotovap with all the bells and whistles. So it's not a lot of money. It's not a GC, it's not a NMR instrument, but neither is it really a trivial expense. So certainly there are groups who would be inspired by the structure of some molecule and say, hey, there's a step that I could design into a total synthesis that would be beautifully conducted using photochemistry. And so they might invest in a $4,000 piece of equipment to try that idea out, or find somebody else in the department who has this piece of equipment. But there are also people who will say, I know a 3 or 4 step route around this particular synthetic problem. So rather than investing the money in doing a kind of slick photochemical technique, maybe what we'll do instead is just kind of go around it and avoid the problem of this purely technological limitation. And so I think that's one of the reasons why synthetic organic chemists who don't specialize in photochemistry have been reluctant to try using these techniques in their lab, or at least it creates this barrier. So we have been working for several years on trying to develop technologies that are activated using visible light. And one of the main reasons behind this is because if you can use visible light in a photochemical reaction, reaction. I mean, we're surrounded by sources of visible light all the time, right? These are some, those are some, the projector is another one. So if you can use visible light, then the cost of the instrumentation that you use goes down significantly. This is the morphology, the photoreactor that we typically use in my lab. It's a $2 compact fluorescent light bulb that we buy from the Home Depot. This clamp light costs about $6. There's nothing special about this setup, incidentally. We've done photochemical reactions using overhead projectors. We've used these blue Kessel lamps that a lot of people are using these days. We run reactions using sunlight coming in through a window. The point being that we are surrounded by photons of visible light all the time. They are cheap. There are lots of sources of them. We happen to use this particular morphology because I want to make sure that reactions are reproducible from one student to the other one. So we agreed early on in my group to use one particular brand of light bulb and one particular shape of this clamp light. But really, there's any sort of light source that you can use to make these reactions go. And so over the past decade, I think what's been really gratifying is that this argument that we made about the accessibility of the instrumentation has really turned out to be a powerfully enabling tool for people to adopt photochemical techniques. So between our group and groups like the Macmillan group and the Stevenson group and the Nisevich group and the Knowles group and so on, who really invested in this idea, I think we've gone to show that there is nothing scary about using photochemistry, that the ability to use these cheaper sources of light to make these reactions go really has helped to accelerate the growth of this field. I will admit, however, that this is a purely technological limitation. And so it's from a chemical point of view, I think there are a lot of photochemists who would say, well, this isn't that expensive. There's a lot of traditional photochemistry that people still aren't using. So I think there's another reason why it is that synthetic organic chemists have been slow to adopt photochemical techniques in real practical synthetic situations. And I think one of the major reasons is the control of stereochemistry in photochemical reactions. So what I'm showing you here is one of the first papers that I read as a graduate student in photochemical synthesis. It's this really beautiful, exhaustive review by Inoue, who is essentially the main player in the field of stereo-controlled photochemistry for many decades before his retirement. It was published in 1992. The first reference listed in it is 1874, so it covers about 120 years worth of chemistry. Nevertheless, it's relatively short, about 30 pages. More importantly, what you find is that of the references that are in this comprehensive review, there are very few examples of catalytic approaches. There are very few examples of enantioselectivities that are significantly high. Most of them are about 10% or lower, and there are some that are just, proof of principle results that give you like 1% TE or something like that. So what you find is that in this review, there are no examples of highly enantioselective catalytic photochemical reactions. And in 1994, that's really remarkable because this was in the heyday of asymmetric catalysis, when there were so many other ways of controlling stereochemistry in essentially every other kind of reaction other than photochemistry. And so, photochemists, it wasn't for lack of trying that the development of this field was so slow. And photochemists recognized that there was probably something that they weren't considering that made the progress in this area so difficult. And what you'll find in a lot of these reviews, both in Inoue's review and also in a more recent review by Bach, is a statement something like the one listed here in blue. Essentially, the idea was that photochemical activation leads to the formation of these highly energetic reactive intermediates by the absorption of the energy in a photon of light. And these energized intermediates are so reactive that it becomes very, very difficult for a catalyst to intercept them and to control their subsequent reactivity. So this is an idea that one might refer to as the reactivity-selectivity principle. The more reactive something is, the harder it is to control its selectivity. And it's a great, intuitively appealing idea, but it turns out that there's no theoretical basis behind it. So here's another way of thinking about it. To get 90% EE at room temperature, you need about 1.5 kilocalories of difference between the transition state energy going to one enantiomer versus the other one, if you believe in transition state theory, wherever Barry is. 1.5 kilocalories per mole of energy is less than the energy it takes to rotate around the central carbon-carbon single bond of ethane. These energies are tiny. So no matter how reactive an organic intermediate is, there is surely some way that you can get a kcal per mole difference between one enantiomer or the other enantiomer of the transition state leading to a chiral product. So we know that there's nothing intrinsic about the reactivity of these species that makes them impossible to control using asymmetric catalysis. Moreover, this is the same sort of argument that people used to make about organoradical chemistry. And in the 1990s and early 2000s was the era when a lot of people like Ned Porter and Mukund Sibi were demonstrating the fact that you can use asymmetric catalytic principles to control the selectivity of radical reactions as well. We also knew that when I was reading this as a graduate student that this wasn't necessarily a killer in the development of asymmetric photochemical reactions, because Thorsten Bach had developed a really beautiful system for controlling the enantioselectivity of a 2+2 cycloaddition in solution. So this paper, published in 2000, was the first example of a highly enantioselective 2+2 cycloaddition reaction in solution that used a source of chirality that was not covalently attached to the substrate and wasn't destroyed in the process. So the first thing that could reasonably be considered a catalyst for an enantioselective photochemical reaction. It's a beautiful, beautiful experiment, right? So it's an early example of hydrogen bonding organocatalysis. The idea is that there's a hydrogen bonding motif on the chiral controller that's complementary to a hydrogen bonding motif on the substrate. So the one-to-one complex exists such that the steric shield blocks the back face of the enone from cycloaddition. So irradiation of the complex allows cycloaddition to only occur from the front face, giving you high levels of enantioselectivity for this 2+2 cycloaddition reaction. So it's a great, great experiment. There's a lot to read into this that I think is really lovely. But it's not a perfect experiment. And I think that even Thorsten would argue that the biggest problem with this entire system is the high, quote-unquote, catalyst loading. You need 2.5 equivalents of the chiral controller to get optimal enantioselectivity. At one equivalent of the chiral controller, the enantioselectivity is about 70%. And at real catalyst loading is like 5%, 10%, or what have you. There really is no enantioselectivity whatsoever. And that really was the clue that got me and my group thinking about how to attack this problem of stereo-controlled photochemistry. To go through this, let me take a step back and walk you through how we think about the design of asymmetric catalytic reactions of any source. I'll use a Diels-Alder reaction as a well-understood example of a reaction that we know how to control using a variety of different strategies for asymmetric catalysis. So normally the way we think about it is that you'll start with some achiral substrate that will bind to a chiral catalyst, and you hope that the stereochemical information on this chiral catalyst, be it a Lewis acid or a organocatalyst or a hydrogen bond donor, that this will differentiate the top and the bottom faces of this enone, such that cycloaddition occurs preferentially from one face to the other, giving you a diastereomerically enriched complex. Then release of the catalyst gives you an enantioenriched product and turns over the catalytic cycle. So these are the important steps of an asymmetric catalytic process. They're the rates that we would measure. They're the transition states that we would compute if you believe in transition state theory. But it's not the only steps that are involved and really important for a highly enantioselective and efficient catalytic system. If you really want good catalysis, you also have to think about the rates of any uncatalyzed background process that might occur. If indeed this is an achiral substrate, then any product that's formed in the absence of the chiral catalyst must necessarily be formed in a racemic form. And so what you're reading out by seeing the enantioselectivity of this overall reaction is a superposition of the rate of the catalyzed process using the enantioselective catalyst that's diminished by whatever proportion of the background reaction that also occurs that generates a racemic product that lowers the enantioselectivity. Now, in the case of the Diels-Alder reaction, this turns out not to be a big problem because a variety of strategies using Lewis acid catalysis or organocatalysis or what have you increases the rate of the Diels-Alder reaction such that this catalyzed process is several orders of magnitudes faster than the background process. So you don't have to really worry about any competition from the racemic background. This is not, however, necessarily the case of photochemistry. The coordination of a Lewis acid, or in Bach's case, a hydrogen bond donor to the enone, doesn't necessarily perturb the photophysical properties of this enone very significantly. And so both the catalyst-bound and the catalyst-unbound form can both react at similar rates to give a mixture of the racemic pathway as well as the stereoselective pathway. Now, if you're using 2.5 equivalents of the chiral controller, then you can force this equilibrium to lie towards the bottom of this equilibrium such that all of the product is being formed via the stereoselective pathway, and you can get gradient anti-selectivities. But at truly catalytic loadings, if you don't control for the rate of the background reaction, at 10 mol%, this equilibrium must lie towards the top, and so the majority of the product gets formed via this racemic background process, leading to overall low enantioselectivities of the product that's formed via these competing pathways. So what we take away from this analysis is that the problem in asymmetric catalytic photochemistry is not the asymmetry. That's reasonably easy. The real problem in asymmetric catalysis of photochemical reactions is the catalysis. How is it that we design strategies to generate product only in the presence of a chiral catalyst under conditions where the free substrate is photochemically silent? And this is really what got my group thinking about visible light photochemistry about a decade ago. If we could learn how to catalyze reactions such that we could make interesting photochemical reactions work using wavelengths of visible light where free substrates don't absorb at all, we can really cut down on the proportion of the product that's being formed via this direct, uncatalyzed photochemical process. So if you're interested in visible light photochemistry as somebody just getting into the field in the first place, an obvious place to begin is to use these ruthenium and iridium photocatalysts that have now come to dominate the field of redox catalysis. I think we now have heard enough about this over the years that I don't have to go into a whole lot of justification for why we use them. I'll just quickly walk through for the students here how at least we think about this from a molecular orbital perspective. So any sort of organic or organometallic molecule that's closed shell, and this is a closed shell D6 low spin octahedral ruthenium complex. So any closed shell intermediate that gets photoexcited, you promote an electron from a filled orbital into what was the LUMO to give you this triplet excited state. Mechanistically, this is really a metal to ligand charge transfer, so you can think about it very simplistically as promoting an electron from a metal-centered orbital out into a ligand-centered orbital to give you this sort of structure. It's oxidized as metal and reduced at the ligand, which is sort of depicted electronically here. But in a simplistic sense, the way you can think about the reactivity of this photoexcited catalyst is the idea that it now has a high energy electron that can be donated to a variety of electron deficient organic species. So this would donate an electron to a low-lying LUMO in a variety of organic species that are electron deficient to essentially do a one electron reduction process, giving you an oxidized metal species. Simultaneously, there's also a high energy vacancy in what was the HOMO of this closed-shelled species. This can accept an electron from a high energy HOMO from a variety of electron-rich organic compounds to do a net one electron oxidation of the organic compound and a one electron reduction of the photocatalyst. So what's been really interesting about ruthenium trisbipyridine and similar photocatalysts over many decades of research is its ability to take the energy in visible light and turn it into electrochemical potential. And so the starting point for us was to think about whether or not we could use the well-studied photoelectrochemical properties of ruthenium trisbipyridine and use it to catalyze interesting photochemical transformations. So we began with this reaction we've now been studying for a decade. It's a 2+2 cycloaddition between this aromatic enone and a partner either intramolecularly or intermolecularly. It begins first the way that all photocatalytic reactions do. Excitation of this ruthenium complex gives you this triplet excited state that I told you is highly redox active. We have good evidence that the first step is oxidation of this tertiary amine to give you an amine radical cation here, and this ruthenium 1 complex that's somewhat more reducing than the triplet excited state here. The reduction potential of this ruthenium complex is on the order of about minus 1.2 volts versus SCE. The reduction potential of this free enone is about 200 millivolts more positive. So, 200 millivolts more negative. So it's about, it's too high in energy to transmit an electron from the reduced ruthenium to the free enone. However, we discovered kind of accidentally that if we add Lewis acidic supporting electrolytes, this lithium cation is really important. This can coordinate to the enone and activate it such that its reduction wave shifts by about 200 millivolts more positive, bringing it into a regime where it can, where it can easily accept an electron from this ruthenium 1 complex, giving you this nucleophilic radical anion. The radical anion can then bond form here, and give you this cyclobutane. And because it's been activated by a one electron reduction, the product still has one too many electrons in it. So to get to the neutral product, you need to lose an electron either by a chain propagating reduction of another equivalent of this enone or a chain terminating reduction of this amine radical cation. So this reaction works really quite well. These are the optimized conditions, consistent with the fact that the key activation step is an electron transfer process. We can only use aromatic enones in this process. So it can be electron rich, it can be electron deficient, or even heteroaromatic. But if we use a symmetrical dialkyl enone, the reduction potential of an aliphatic enone is about 600 millivolts more negative than that of an aromatic one, because the corresponding radical anion is much less conjugated and therefore harder to form. But we only need to have one aromatic group. So if one side is aromatic and the other side is aliphatic, the reaction works fine. It can be an ester or an amide. We can even do intermolecular reactions. My student, Joanna Du, who was one of the first students to join this project, looked at the substrate scope and designed this experiment to show that we can do crossed intermolecular 2+2 cycloadditions as well. So in this experiment, we're using the same optimized photocatalyst conditions. One of the two enones here is aromatic, so it's much easier to reduce than the corresponding aliphatic enone. So when you shine light on this catalyst system, you reduce this compound and make a nucleophilic radical anion. Then when you form the nucleophilic radical anion, it has the choice of reacting either with another equivalent of itself or with this aliphatic enone. The aliphatic enone, even though it's harder to reduce, has no beta substituent, so from a steric perspective is much more electrophilic. So this is the generated nucleophile, this is the selective electrophile, so you get really good cross-selectivities with absolutely no homodimerization of the aliphatic enone and just trace amounts of the homodimerization of the aromatic enone that you can outcompete simply by increasing the concentration of methyl vinyl ketone and then get a single product and good yield and good diastereoselectivity. Or once again, we can change the aromatic group, we can change the beta substituent, we can also change the Michael acceptor as well and get these interesting crossed 2+2 products. So mechanistically, I guess the way that we think about how this catalyst system works is that it's a two-catalyst system. One of the catalysts is the photocatalyst, whose job it is to take visible light energy and turn it into electrochemical potential. The role of this Lewis acid catalyst then is to activate the substrate, make it more electrophilic, and stabilize the corresponding radical anion. And if you've got a system where you've got two different catalysts, and you want to design an asymmetric catalytic version of the reaction, you can obviously put stereochemical information conceptually on either one of these two catalysts. But we really quickly realized that where we wanted to focus our attention was not on the photocatalyst, but rather on the Lewis acid catalyst. And the main reason for that was something that I just mentioned earlier, which is that this is a chain process. This ketyl radical is a strong enough reductant to reduce another equivalent of the starting material. And so we've actually measured the length of these chains. They're about 150 steps long at a minimum. And so they're really efficient chain processes. So if you put all of our stereochemical information all on this ruthenium complex, then you might get good EE in the first turnover, but all of the subsequent turnovers would happen in the absence of the photocatalyst and therefore happen via a racemic pathway. So this seems like a bad idea for putting stereochemical information on the photocatalyst. However, the role of the Lewis acid is more general. What it does is it activates the substrate towards one electron reduction and stabilizes the corresponding ketyl radical. And so we imagine that that Lewis acid catalyst might be involved in every turnover of the chain process. And so we started a campaign of trying to design a chiral Lewis acid as a co-catalyst for this photochemical 2+2 cycloaddition reaction. And it took a while for us to develop this. It was about a 4-year process all told. But what we ended up with was this 2+2 cycloaddition reaction, still using ruthenium trisbipyridyl as the photocatalyst, but now a chiral Lewis acid that was generated in situ by the coordination of europium triflate and this kind of unusual Schiff-base dipeptide ligand. So this was synthesized via, or discovered via kind of a combinatorial process. We synthesized about 70 different dipeptide ligands with different kinds of Schiff-base capping groups on them, and this was the one that gave us the highest enantioselectivities. The enantioselectivity is good. The scope of the reaction is essentially the same. But more important than the scope, I think, is the fact that if you look at a relationship between the loading of the chiral Lewis acid and the overall enantioselectivity, obviously as you drop the amount of the chiral Lewis acid you're using, the rate of the reaction goes down. But the enantioselectivity is the same from reaction to reaction to reaction. And what you take away from that is that there's no longer a relationship between the loading of the chiral controller that you have and the EE of the product. And the reason for that essentially is that we've done what we set out to do. All of the product here is being formed via the catalyzed process because we've shut off the background process altogether. Another feature of this that I think was equally important that we didn't think about when we were originally designing the process is the fact that we really did have to optimize the structure of this chiral ligand pretty extensively. This, like I mentioned, it took about 4 years to discover this, this co-catalyst. We decided to optimize around this because this is a class of ligands that was really popularized by Hoveda, specifically because you can synthesize these combinatorial libraries relatively easily. And what we noticed as we were screening this family of about 70 different ligands was that, of course, the enantioselectivity changed from ligand to ligand to ligand, but the overall rate of the reaction didn't change all that much. And that actually turns out to be something that's non-obvious, but really quite important. So when you look through the history of attempts to control the enantioselectivity of photochemical reactions using chiral catalysts, typically what people have done is they've tried to design a single chemical entity that's both a photocatalyst as well as a chiral controller. Now, for those of you who've done asymmetric catalysis, you know that it's very rare that the first structure that you try as an asymmetric catalyst is the best enantioselective catalyst that you have. You need to change the structure to, change an isopropyl group to a tert-butyl group to a phenyl group to what have you, to really shape the transition state to give you high enantioselectivities. Those of you who've done photochemistry, maybe you've done something with a fluorophore, you also know that an organic fluorophore is incredibly sensitive to structural perturbations. And the changing of a methyl group to an isopropyl group to a phenyl group to what have you can completely change everything about its photophysical properties. So in those cases where you have a single chiral photocatalyst, what you really have to do is hit a sweet spot where both the chiral controlling elements and the photophysical properties both line up in the same compound. Here what we've done is we've separated out the chiral controller from the photocatalyst so that we can change the structure of the chiral catalyst as much as we want to and really tune for high enantioselectivities without perturbing the photophysical properties of the photocatalyst. And so one of the things that came out of this was that we could discover new reactivity. If we take this imine ligand and simply reduce it to the corresponding amine, we still get 2+2 cycloadducts with good enantioselectivities, but now we get the cis selectivity across these two carbonyls rather than the trans selectivity. And so now we've got a system that gives you good control over both the absolute as well as the relative stereochemistry of this 2+2 cycloadduct. Okay, so like I mentioned, the main role of the chiral Lewis acid is to catalyze this electron transfer process that's the key activation step in these photoreductive, photoredox processes. It turns out that the use of Lewis acid co-catalysts in photoredox reactions seems to be a reasonably general process. I'm showing you 3 examples from my lab. Here, this is a 3+2 cycloaddition that we published several years ago. They're synthesized, the substrates are synthesized via Corey-Tchaikovsky cyclopropanation of the same enones that we had optimized the 2+2 chemistry around. Now, by cyclopropanating this double bond, it's much less conjugated, the radical anion is less stabilized by resonance, and therefore we have to compensate for its more negative reduction potential by using a stronger Lewis acid. It turns out that lanthanum triflate is empirically the optimal one here, and this allows us to reduce the aromatic ketone to the corresponding ketyl radical, which fragments and adds across this double bond to give you a new 5-membered ring. This is a radical anion 4+2 cycloaddition reaction where we found empirically that magnesium perchlorate was the optimal Lewis acid that balanced the rate of productive photoreduction of the enone without over-reduction of the product to lead to reductive cleavage of the sensitive carbon-oxygen alpha bond. This is an example that shows these are essentially the same substrates that we'd optimize the 2+2 chemistry around, but if we use a Bronsted acid instead of a Lewis acid, rather than getting 2+2 cycloaddition, we now begin to see this reductive coupling product where we only form this beta-beta bond, but not this alpha-alpha bond, giving you a completely different product with different stereochemistry and different redox balance. So the idea here is that when you've got a co-catalyst in these photoredox processes, you have another knob that you can turn to optimize these reactions and get better selectivities, better reactivities, or sometimes even just change the overall course of this reaction. But the fact that Lewis acid catalysis seems to be a general process in photoredox processes also got us thinking about whether or not we can discover enantioselective versions of all of these reactions that use chiral Lewis acids as a co-catalyst. And this has turned out to be a major theme of what we've done over the past 10 years. This is a paper we published early last year. It's an enantioselective version of this 3+2 cycloaddition reaction in an intermolecular fashion. We've used still ruthenium trisbipyridyl as the photocatalyst here, but we're now using this gadolinium pi box complex. It's kind of unique. I mean, it's a different Lewis acid metal center than we used in the 2+2 chemistry. It's a different family of chiral ligands, so we can really change the structure of the Lewis acid. But you'll also notice how much we've had to tune the overall structure of this pi box. Importantly, we had to introduce this dimethylamino group at the para position of the pi box to control the Lewis acidity of the gadolinium, of the gadolinium center. And this is the sort of thing that is done pretty commonly in Lewis acid catalysis, but really couldn't be done if the Lewis acid catalyst was also a chromophore. The introduction of a dimethylamino group is a common thing that one would do to a fluorophore to completely quench all of its fluorescence. And so the fact that we can make these relatively large changes to the structure of the chiral controller is something that's possible only because we've separated out the chiral controller from the photocatalyst. This is another paper that we published a couple of years ago. Now it's a photooxidative process. We're still using ruthenium trisbipyridyl to oxidize this alpha-silylamine to the corresponding alpha amino radical, chemistry that was pioneered by Pat Mariano. The role of the chiral Lewis acid, now it's a scandium pi box complex, is not to catalyze electron transfer, but rather to catalyze the addition of this nucleophilic alpha amino radical in a Gizeh addition to this Michael acceptor, again in good enantioselectivities. activities. The important point here, so for those of you who are aficionados of asymmetric catalysis, you might recognize that this is a somewhat unusual auxiliary group on the Michael acceptor. It's the chiral relay auxiliary that was developed by Mukund Sibi specifically for this kind of Gizeh addition, where the transition state is very early, and so the bond is being formed really far away from the stereochemical information on the chiral catalyst. The fluxional nitrogen stereocenter here transmits the stereochemical information closer out to where that bond is being formed, and is really critical for high enantioselectivity in this reaction. So an important point that I want to make with this slide is that, we really do understand a lot about chiral Lewis acid catalysis in asymmetric catalysis. And the fact that we can take all of this insight from 20 years of development in chiral Lewis acid catalysis and bring it to bear in photochemistry, I think is a major, major strategic advantage of this two-catalyst approach that we've been using. I couldn't go further without mentioning that, it seems like dual catalysis, which has been a theme of asymmetric catalysis in my group, also seems to be general in a variety of other groups. So this is the first example of an organocatalytic photochemical reaction published by Dave Nisevich when he was a postdoc in Dave McMillan's group in 2008. Here, the role of the ruthenium is to reduce the alpha carbon-bromine bond to a corresponding electrophilic alpha-keto radical. This reacts with an enamine that's generated by condensation of a secondary amine organocatalyst with this aldehyde, giving you net alkylation and good enantioselectivities. Again, being able to tune the structure of the organocatalyst here was absolutely critical. And in one of my most favorite examples, this is a paper published by Rob Knowles early on in his career. Here he uses this iridium photocatalyst that's very much like rubibia, just has a longer lifetime than the ruthenium complexes do, and now a Bronsted acid catalyst that participates in proton-coupled electron transfer to give you these ketyl radicals, and then the chiral anion controls the enantioselectivity of this reductive coupling to give these amino alcohols, again, good yields, good enantioselectivities. So this idea of using a secondary chiral catalyst from organocatalysis or Lewis acid catalysis, or in some cases also transition metal catalysis, to develop highly enantioselective versions of these photochemical reactions, I think is a major, major step forward in the ability to use this entire class of reactions in modern contexts. Now, what I do have to admit about all of this chemistry is that as my group has been developing it for the past decade, we've always been a little bit cautious about really calling it photochemistry. And when I've talked to photochemists about what we've been doing, they'll acknowledge this is a kind of photochemistry, but they would refer to them as secondary photoreactions. That is to say, the reactive intermediate in all of these cases, whether it's this 2+2 reaction or this amine addition reaction or this organocatalytic alkylation reaction, in all cases, the reactive intermediate is one that's generated by a photoredox electron transfer to generate some open-shelled radical species. But then the important key bond-forming step happens from an open-shelled reactive species in its electronically ground state configuration. That is to say, we're not really doing excited state chemistry. Now, there are a lot of ways of making radicals. I would argue that photoredox catalysis is probably one of the nicer, most general ways of making a variety of different kinds of radicals, but there are a lot of chemical oxidants and reductants or other more traditional ways of making organic radicals. So by developing this strategy for controlling photoredox reactions, have we really solved the problem of controlling electron excited states? And in fact, on that very first slide where I was telling you about the specific kinds of reactivity you get in electrocyclization reactions and the Woodward-Hobson orbital symmetry rules, these are really rules that apply to electronically excited states. And these are not electronically excited states. So in primary photoreactions, where the bonds are being formed directly from electronically excited organic intermediates, there are very, very few successful strategies that use asymmetric catalysis to control their stereochemistry. I'm showing you one of the best, again by Thorsten Bach. Here he uses this chiral oxazoborolidine to coordinate to this enone, and that catalyzes a photochemical 2+2 cycloaddition reaction with reasonably good enantioselectivities. selectivities. Where this comes from is something that Fred Lewis discovered many years ago, which is that in some cases, the coordination of a Lewis acid to an enone will change its absorption properties, so it shifts the absorption of the free enone by, I guess, about 100 nanometers, more to the red. And so if you're very careful and irradiate only this shoulder, you can get selective excitation of the Lewis acid-bound complex selectively over the free complex. Now, this is a great paper. It's one of my favorite papers in the literature. However, it's not a very general process. Bach has only discovered, I think at this point, 4 different enones that participate in this process that have this same sort of redshift in their absorption properties. And even so, that's a relatively small change, such that there's always still some background irradiation, which requires the use of relatively high concentrations of the chiral Lewis acid to outcompete direct excitation, which of course leads to racemic processes. So, my group had really been trying to think about how to use this dual catalyst strategy to control the reactivity of electronically excited states, and we didn't know how to. So we kind of stumbled into a solution accidentally. And it came in the context of a reaction that we were trying to solve that was inspired by a series of reports by John Porco at BU. So John got interested in a class of natural products that arose from Diels-Alder reaction between a variety of these naturally occurring 2' hydroxyl flavones that undergo Diels-Alder reaction to give 4+2 cycloadducts with a variety of dienes, that terpene-derived dienes that are ubiquitous in plants. And so he developed 2 different systems. One of them was an overall reductive system where the idea is you generate a cobalt-1 species that reduces the enone to the corresponding ketyl radical. And this, Porco argued, was activated towards 4+2 cycloaddition to give these Diels-Alder products. The second paper, published a couple years later, instead uses silver nanoparticles. Silver nanoparticles are somewhat oxidizing, and he had good evidence for the formation of these phenoxy radicals upon absorption of the 2' hydroxychalcones onto the surface of these silver nanoparticles. And so here, a photooxidative event leads to the formation of this phenoxy radical that again activates the enone towards 4+2 cycloaddition reaction. So I was really interested in this system because it seemed like an obvious place to try our dual catalyst system, where we use a photoredox catalyst to generate either the radical anion or the phenoxy radical. And then in both cases, there's some kind of metal interaction with this chelating 2' hydroxychalcone that we thought we might replicate by using a chiral Lewis acid. And so, I've just told you a lot about how we thought about the formation of these ketyl radicals using photoredox catalysis. It turns out we actually also know a lot about the formation of phenoxy radicals. Travis Bloom's first project in my group was this 3+2 cycloaddition reaction. I won't go into too much detail, but the key step here is that this catalyst system generates a highly oxidizing ruthenium species that will oxidize this phenol to the corresponding phenoxy radical, and that undergoes spontaneous 3+2 cycloaddition to give you these dihydrobenzofurans that are at the heart of a variety of natural products. So the point is, essentially, that we know that photoredox catalysis is both good at making ketyl radicals as well as making phenoxy radicals. So after finishing this process, Travis got interested in trying to see if he could replicate this 4+2 chemistry that Porco had originally reported using our strategy of using dual photoredox catalysis. And so in the presence of just ruthenium trisbipyridyl, he could take this hydroxychalcone and this diene, combine them, and there really was no reaction upon irradiation. And then as he began to add a variety of different kinds of Lewis acids that hopefully would chelate to the substrate and hopefully make it easier to reduce, rather than seeing the 4+2 cycloadduct, he began to see this somewhat annoying 2+2 cycloadduct, and we really could never optimize around it. So instead, Travis got to the point where he just wanted to see if he could optimize for the formation of this 2+2 cycloadduct. It turns out to work a little bit better when you use catalytic scandium rather than stoichiometric scandium. And it's, again, this dual catalytic process where if you leave out the photocatalyst or you leave out the Lewis acid, there's no reaction whatsoever. And so obviously, if you have this sort of dual catalyst system, it's an obvious question to ask whether or not you can use a chiral Lewis acid. Here it's a scandium pibox complex. Again, ruthenium trisbipyridyl is the photocatalyst. And we get great enantioselectivities for the formation of these 2+2 cycloadducts to give these vinyl cyclobutanes. Again, we can change what the diene is. We can also change what the chalcone is, both on the aromatic ketyl ring as well as the beta substituent. This was an accidental discovery, and so I think I have a hard time arguing that synthetically this is important transformation, although I would say that if you're a medicinal chemist, this is a pretty interesting scaffold, right? Cyclobutanes are somewhat difficult to make. We've set 3 different stereocenters on that ring with good enantioselectivity. But I think what really intrigued me and Travis most was exactly what's going on in this reaction. And there's a lot about it that told us that there was something funny about it, that it didn't really seem like a photoredox reaction. Now, one of the things that I would say about that is that, in photoredox reactions, one of the really powerful things about the strategy is that after 50 years of research into the photochemistry of rubipy, there are now hundreds of rubipy analogs with different sort of ligands on them that really finely perturb the electrochemical potential of these photocatalysts. And that's been important both to my group as to a variety of other groups that study photoredox catalysis. But what we found that was really interesting is that there really didn't seem to be a correlation between the redox potential of the photocatalyst and the overall efficiency of this reaction, which is unusual for a reaction that's initiated by electron transfer. Marcus theory tells us that, to a first approximation, there should be some relationship between the rate of electron transfer and the driving force you apply to it. But both more oxidizing photocatalysts and more reducing photocatalysts were sometimes pretty good, sometimes they were pretty bad, but we could never really pull out a very good trend. So that was interesting. Another thing that was really interesting was that, if this is a photoredox reaction, I mentioned there's a lot of chemical one-electron reductants and oxidants. And as a test, we will often test photoredox reactions by trying to replicate the reactivity using a chemical redox reagent, either a one-electron reductant or a one-electron oxidant. And in this particular case, we could never replicate this 2+2 chemistry using a chemical redox reagent. So that was interesting. In fact, the only example of another set of conditions where we were able to form this 2+2 cycloadduct was also photochemical. And it was in the use of a variety of different kinds of triplet sensitizers, in this case, naphthol ketone, which is a pretty well-studied triplet sensitizer in classical photochemistry. Here we got the same 2+2 cycloadduct. It was a longer reaction. It required higher catalyst loadings, but nevertheless, we got the same product, and importantly, in the same enantioselectivity. And asymmetric catalysis is so sensitive to changes in enantioselectivity that we reasoned, if we're getting the same product with the same enantioselectivity using a classical triplet sensitizer, it was probably the case that rubipy in this reaction was also serving as a triplet sensitizer. So I think triplet sensitization hasn't gotten the same sort of impact at this point as photoredox chemistry does. This is how we think about it. This is just another way of depicting the triplet excited state of rubipy here. Again, it's this sort of this open-shelled triplet species that has this high energy electron that can donate as well as a high energy vacancy that can oxidize. And if either of these 2 electron transfer processes happens independently, that's a photoredox step. Another way that these photocatalysts can activate an organic molecule is by essentially bilateral electron transfer. So this electron hops over here, this electron hops over here, and what that gives you is not an overall redox process, but an energy transfer process, where this triplet collapses with concomitant formation of the triplet excited state of the organic substrate. So since both of these electron transfers are happening simultaneously in a coupled way, it's no longer the redox potentials of the individual electron transfers that dictates whether or not these reactions are feasible or not. Instead, it's the thermodynamics of the overall state change. This process is feasible only when the triplet excited state of the photocatalyst is higher in energy than the triplet excited state of the substrate that's being activated. So we've been showing for the past several years that the same classes of iridium and ruthenium photocatalysts that everyone is now using as a photoredox catalyst also are exceptional triplet energy sensitizers as well. This is an example of a 2+2 cycloaddition reaction where we start with a diene. And I like this because dienes are hard to reduce, they're hard to oxidize, they're well outside of the range of any of the photoredox catalysts that we use in my lab. And so we can never activate dienes directly using photoredox chemistry. However, the triplet excited state of a diene is only about 55 kilocals per mole. And there are a variety of iridium complexes that have triplet energies that are well higher than the triplet energies of a diene. So using this fluorinated iridium complex, we can activate this diene via energy transfer, which then undergoes 2+2 cycloaddition in a primary photochemical process. We also have used this iridium photocatalyst as a way of sensitizing these acyl azides to generate triplet nitrines. These nitrines will undergo aziridination reactions again in good yields using this in a primary photochemical process. So we know that the same classes of photoredox catalysts that are really great for electron transfer are also really competent at doing really competent at doing energy transfer as well. And all of the photophysical properties that make them exceptional photoredox catalysts also make them really fantastic energy transfer catalysts as well. So to kind of think about what the mechanism of this reaction might be, we went back to this square kind of mechanism. We already knew that the direct photochemical reaction was thermodynamically not very feasible. And that's because we know the triplet energy of the ruthenium complex that we used. It's about 45 kilocals per mole. You can find this easily in the literature. You can also directly measure it by looking at the energy of the photons that are emitted by phosphorescence from these complexes. The energy of the photon that comes out from the triplet excited state is more or less the energy of the triplet excited state. Okay? So it's about 46 kilocals per mole. The energy of the free chalcone itself turns out is harder to measure. It's not really emissive on its own, but nevertheless, we went into the literature and we found an experimentally determined value for the triplet energy of the 2' hydroxychalcone that is about 10 kilocals per mole higher than the energy of the triplet excited state of this ruthenium complex. And so energy transfer from the triplet state of rubipi to the hydroxychalcone should be unfavorable by about 10 kilocals per mole. And indeed, in the absence of a Lewis acid, we see no energy transfer and no reaction. So what we posited was that perhaps the coordination of a Lewis acid to the substrate will change its electronic properties such that the triplet excited state is much lower in energy, turning on the feasibility of energy transfer from the photocatalyst to a lowered energy Lewis acid hydroxychalcone complex. And so we spent a really long time trying to find an emission from the Lewis acid complex, and we never could really find anything. So ultimately, Travis ended up talking to a staff scientist at Wisconsin, Desiree Bates, who's a computational chemist, whose job it is to teach ignorant organic chemists like us how to do computations. And he basically went and tried to find a DFT functional that would more or less replicate the energy of the triplet excited state of the free substrate that had been reported in the literature. And it turns out that this basis set is the one that gave us reasonably good agreement with the literature report. And then used that same functional and applied it to try to compute what the triplet excited state of the scandium complex might be. And he found that indeed the energy of the scandium complex was predicted to be about 20 kilocals per mole lower in energy than the free substrate. So easily in the range where it could accept energy from the triplet excited state of rubipi, which is about 45 kilocals per mole. In fact, this energy was so low that it turns out that it was one reason that we might not have seen emission from it was because the fluorimeter we were using to try to find the phosphorescence of this complex stopped well before 32 kilocals per mole. And so what Travis had to do was he had to go across the street to the material science lab to find somebody with a near IR detector that could actually observe emission from these scandium complexes, and this is what we got. In black is the emission from the free substrate by itself, and as you can see, there's really no emission there whatsoever. In red is what happens when we add scandium. And the energy of the photon coming from the triplet excited state is more or less exactly what we predicted it to be by DFT computation. We can also validate that it's coming from a triplet excited state because if we try to do the same measurement in the presence of oxygen, the phosphorescence is diminished pretty significantly by the addition of oxygen. So that seems consistent with the triplet emission and not a singlet emission. So overall, you know, I think this is really exciting. We seem to have discovered a new physical effect that leads to a different way of thinking about how to catalyze photochemical reactions that involves the reactivity of triplet excited states. And so now what we're doing is to try to figure out whether or not this accidental discovery is something that we can generalize. So one thing we've been doing recently is to ask, well, what other reaction partners other than dienes work? It turns out that styrenes are also fantastic reaction partners in these enantioselective 2+2 reactions. Enantioselectivities are even higher than they are with dienes. And this is nice because there's a relatively small class of natural products that look more or less like this. They're neolignin cyclobutanes. And this seems to be a really direct way of synthesizing them. BJ just finished the synthesis last week. The key point is the photochemistry works quite well, but we have to cleave off this aryl ketone. And the electron rich nature of these aromatic group means that we can't use traditional oxidative cleavage methods to take it off. So instead, BJ came up with this really slick two-step process where he does first a courteous rearrangement to get to this benzoxazole, and then hydrolysis to give you the carboxylic acid. And then we simply install the last methoxy group via a Buchwald Hartwig coupling using rock-phos to give the final natural product. So we think this is a really useful way of synthesizing a class of natural products that I don't think was accessible synthetically before. More importantly, though, is whether or not there's something special about the hydroxychalcone moiety that's, I guess, kind of unusual in asymmetric catalysis. And we don't think this is, that it is something special. So Mary Beth, who gave a poster on Sunday and won the poster award on that first day, her project has really been all about trying to test whether or not we can activate other kinds of enones. And I'll show you just a couple of key experiments that suggest that we probably can. So the triplet excited state of cinemates is really quite high, and so consistent with that, we really can't get any energy transfer in a very efficient manner from the triplet excited state of an iridium photocatalyst to this species. So in the absence of a Lewis acid, there's no 2+2 cycloaddition. If we add a Lewis acid, we get a pretty good turn-on of reactivity to get these sorts of compounds using even catalytic aluminum. And in a couple of preliminary experiments, Mary Beth has also shown that you can use these oxazoborolidines to catalyze these reactions with reasonably good enantioselectivities. So we're continuing to work on this, but I think the important part here is that there really doesn't seem to be something special about the hydroxychalcones. And what's really exciting is that, you know, these cinemates aren't the only substrates that Mary Beth has shown we can turn on triplet energy transfer to. And so if this turns out to be something general, then I think what we have is a really robust way of controlling the enantioselectivity, not only of photocatalytic reactions that are induced by photoelectron transfer, but also by energy transfer as well. So maybe having a more robust solution to these primary photoreactions as well. So let me finish with maybe one sort of off-the-cuff remark here that is inspired by some of the earlier talks. I think a lot of us have been kind of trying to argue against this notion that organic chemistry is done, or that organic synthesis is a mature field, or whatever that means. I guess what I would challenge back is, how would you know, right? I mean, so when I began as a graduate student, you know, I really wanted to study synthetic photochemistry. And when I went to all of these different schools to try to find someone to work with who was doing synthetic photochemistry, there were two. There was Paul Wender, and there was Eric Carrera, who I ended up going to work for. You know, there was a period in the 80s and 90s when synthetic organic photochemistry was in its heyday. Like, there were a lot of people really studying this problem. And then in the 90s and the early 2000s, people really began to say, well, you know, photochemistry is dead. There's nothing else we're ever going to get out of photochemistry. You're never going to be able to control its stereochemistry. And my question would be, well, how do you know? And so I just waited until I had my own group to begin to ask these questions of whether or not we could really use the same principles of catalysis that have been so powerful in other kinds of reactions and try to apply those to photochemical reactions. And it turns out that it works. So I guess what I would say to those of you who are students, either graduate students or undergraduate students, you know, there's some reason you love chemistry right now, and you're going to read blogs and you're going to read Twitter streams that tell you that this kind of chemistry is dumb or that kind of chemistry is dumb. Please don't listen to them. Love the stuff you love, and teach other people why it's important. Okay. I don't know where that came from. So, let me finish by thanking the people that I'm really privileged to work with. So I have an amazing team of people at UW. I've tried to mention their names as I go through. In blue over here, this is the photo redox team. In pink over here is the energy transfer team. The photo redox stuff was really started out by this team of Joanna Du, Kaz Scooby, and Danny Schultz. They were on that first publication that showed that we can do asymmetric dual catalysis to control 2+2 cycloaddition reactions. Adrian developed the 3+2 chemistry. Laura did the conjugate addition chemistry. All of that energy transfer stuff that I finished up with was the PhD work of Travis Bloom, who stuck with this project even though I kept trying to tell him that I wasn't interested in the 2+2 chemistry. Could he please make the 4+2 chemistry work? And he still turned this into an entire other area. BJ and Zach explored the generality with respect to other coupling partners, and BJ is the one who finished the total synthesis. Mary Beth I already mentioned, she's the one trying to look at the generality with respect to other substrates in this Lewis acid catalyzed process. And Evan did some work I didn't talk about, but he's trying to show that Bronsted acids also work in a similar kind of way. So they're part of this great team that I have at Wisconsin. I need to thank all of them. Thank these people for funding this research, and once again, thank you very much for your attention.
Thank you so much, Professor Yoon. Questions? This one. Professor Carpenter.
Oh, no. I was just complaining that this is my nightmare, that you were going to ask me the first question, but please.
And it has nothing to do with transition state.
Oh, thank you.
It actually has to do with the triplet energy transfer, and
Yes.
I wonder whether your Lewis acid catalyst isn't doing something additional that you didn't talk about. So what I'm thinking is, once you've done the triplet energy transfer, and you want to do your cycloaddition, if that cycloaddition were occurring in just a simple organic molecule, you wouldn't expect it to be stereoselective, because you can't do an adiabatic cycloaddition. The triplet excited state of the product is too high in energy. So somewhere along the way, there has to be an intersystem crossing.
That's right.
And usually, in organic molecules, that's sufficiently slow.
Oh, I see what you're saying.
That you make the bonds one at a time and you lose stereochemistry.
That's great.
So I wonder whether your Lewis acid catalyst isn't also facilitating intersystem crossing,
That's
and that's actually a key part of getting stereoselectivity.
I think that's a really fascinating idea. I really hadn't thought about it that way. So essentially the idea being that it's serving as a heavy atom that helps with the intersystem crossing. That's really interesting. Yeah, I don't think we have any experimental evidence that would be able to speak to that. What we do have is I have a collaboration with Mookie Bake at KAIST, who's helping us to kind of probe the energetics of these mechanisms. And what he's suggesting, I guess we haven't really looked at the intersystem crossing from the putative 1,4 diradical. But what he has shown is that essentially the dynamics of the Lewis acid catalyzed process are completely different. Right? That in most cases, the energy of that first bond formation is actually much higher. And so it's much slower. So essentially what we're catalyzing is the activation of the substrate, but then everything else the substrate does is actually a bit slower. But the idea of it influencing the rate of intersystem crossing is something we hadn't thought of at all. And that's really a really clever one. Thank you. That's a great suggestion.
Hi, Professor Yoon.
Yes.
So it was a beautiful talk. So I want to ask a question about the energy transfer. So you had a catalyst. So how about the catalyst design? So when energy transfer happens, the molecule has to come close together. Have you look at that, like how the design of the catalyst affect those reactions?
Yeah, that's a great question. Yeah, so this is a great question. So essentially, in all of these cases of energy transfer, the energy transfer is more or less collisional. You need for this relatively short-lived excited state of the photocatalyst to interact with the organic molecule, and it needs to live long enough to kind of bounce into an organic molecule in the right sort of orientation that molecular orbitals line up and you get this energy transfer. So one thing we've been thinking about a lot recently is whether or not we can design photocatalysts, and I think this is the heart of your question. Can you design photocatalysts that will recruit the organic molecule to them, right? And so sort of like accelerate that rate of energy transfer. The answer is yes, and we're beginning to put together that paper right now. So wait a couple of months, and hopefully you'll see that result.
Thank you.
Any other questions? If not, let's thank Professor Yoon again for an inspiring talk. presentation. Thank you.